Okay, today we're talking about section 4.2, which is adding, subtracting, and multiplying polynomials. And then additionally at the end, we'll have the binomial expansion theorem, which makes use of Pascal's triangle. Okay, so first of all, just to go back to the basics, what is a polynomial? A polynomial is anytime you have a variable like x raised to the power of an integer, right? So x to the first, x to the second, x to the third, x to the fourth. Now, the variable doesn't have to be x, it can be any variable, a, b, c, d, e, f, g, whatever you want. But the important part is that the exponent is an integer and not another variable, or not a fraction, or not a negative number, right? It's going to be a positive integer. Okay, so here's an example of a polynomial. You could have like 2m to the fourth plus 3m cubed minus 5m squared plus 6. There's a polynomial. The reason it's a polynomial is because there are multiple terms within that given polynomial. Poly meaning multiple. Okay, so this whole chapter is about adding, subtracting, and multiplying polynomials. And remember, when you're adding and subtracting polynomials, you can only combine like terms. Okay, so what's a like term? A like term is when both the variable and the exponent are the same. Okay, so I can add x squared and 2x squared because the variable x and the exponent 2 are both the same. Now, what is not a like term? If I wanted to do x squared plus 2x, where now the exponent on that second term, x, is what? What's the exponent on that? If you don't see it, it's just a 1, right? It's an imaginary 1. So now the exponent is not the same. I cannot add those. Those are not considered like terms. I can't subtract them either. Okay, so in order to add or subtract polynomials, the terms have to be the same. Okay, let's look at a couple examples of some like terms. So something like 3a and negative 6a. Those are like terms. The variable and the exponent are the same. Notice the number in front does not have to be the same. The number in front, called the coefficient, can differ between the two terms. Okay, so another example of some like terms, we could have n to the fourth and 6n to the fourth. Okay, the variable and the exponent are the same. Those are like terms. Let's do one more example, this time of what are not like terms. This next example, these are not like terms. Okay, so how about 6x to the 7th and 9x to the 5th? Those are not like terms. Why? Because the exponent is not the same. Okay, perfect. Now, when you're multiplying, and let's do a couple of quick examples really quick with the adding and subtracting. So 3n to the 4th plus 5n to the 4th. That would be 8n to the 4th. 6x squared minus 10x squared, that's negative 4x squared. Do you see how I'm simply just combining the numbers in front? 3 plus 5 is 8, 6 minus 10 is negative 4, and then I leave the term that I started with between the two like terms as the ending part of that. Okay. Now, when you're multiplying polynomials, you can multiply any terms together. They do not need to be like terms. Okay, so let's look at multiplying polynomials. So let's say I had x to the power of 2 times x to the power of 3. These are not like terms because the variable is not the same. Or sorry, because the exponent is not the same, but I can still multiply these. And do you remember, when I'm multiplying variables with exponents, what do I do to the exponents? I add them, right? So this would be x to the 2 plus 3, which is x to the 5th. Okay. What if I wanted to do 6m times 3m to the 4th? 6m times 3m to the 4th, I just multiply the two numbers in front, the coefficients, 18, and then I multiply the variables. M to the power of 1, if you don't see a variable or an exponent there, it's really just a 1. M to the power of 1 times m to the power of 4 is m to the power of 5. Okay, let's get rid of those. What if I did something like negative 10 times 5x squared? Well, negative 10 times 5 is negative 50, and you just bring the x squared there. Okay, there's something I want to show you really quick. Negative 10 is really the same as negative 10x to the 0. I know that seems weird. Why is that? Because anything to the power of 0 is just 1. So negative 10x to the 0 is just negative 10 times 1. So really there is an x term there. It's just hidden because it's to the power of 0. So negative 10 times 5x squared is just negative 50x squared. I can just take that number, multiply it by the coefficient, and leave the x squared there. Great. So the terms do not have to be like terms in order to multiply them. All right, let's do a couple of examples here. So on this first one, we're going to be adding these two polynomials together. Okay? So let's take a look. Starting with my first term on the left, 12x to the fifth. Do I see any like terms on the right? Do I see any variables that have a power of 5? The answer is I do not. So there is no like terms, so I'm going to leave 12x to the fifth alone. Can't do anything with it because there's nothing to combine it with. Next thing, negative 3x to the fourth. Do I see any x to the fourths on the right side? Yes, I do. 8x to the fourth. So I'm doing negative 3x to the fourth plus 8x to the fourth. Negative 3 plus 8 is 5, so positive 5x to the fourth. Okay? And I like to cancel. I like to cross things out when I'm done with them so that I know what I have looked at and what I have not looked at. The next thing I'm looking at is my 2x, okay? On the right-hand side, do I see anything with just an x to the power of 1 like I have right here? Yes. 4x. 2x plus 4x is 6x. So 2x and 4x are 6x. And now I'm to my constant, which is just the number. There's no variable attached to it. Negative 5, and on the right I see a positive 1. Negative 5 and plus 1 are minus 4. Okay? Now notice, there's something on the right-hand side that I didn't combine with anything on the left-hand side. This term right here. I can't just forget about that. I have to add that in because otherwise my answer would not be complete. So I'm going to put that in here at the end. The negative 3x to the third. Now there's something I want you to note. This is not in its most proper form. To have a polynomial written in the most proper form, you want to have it in decreasing order from highest exponent to lowest exponent. Okay, so I'd want to rearrange this and make it 12x to the fifth plus 5x to the fourth minus 3x cubed plus 6x minus 4. Notice how I brought that 3x cubed right after the x to the fourth to make it in order of decreasing. Okay, that's called standard form. All right, this next one, I'm subtracting these two polynomials. Okay, so when you're subtracting polynomials, I feel like the easiest way to go about it is to look at the negative sign before the second polynomial and just distribute that negative to every term inside the parentheses. Okay, so what does that look like? So I'm just going to rewrite my first polynomial, 11x to the fourth minus 9x squared plus 3x plus 11. And then I'm going to distribute that negative in. So negative positive 2x squared becomes negative 2x to the fourth minus 6x cubed minus 2x plus 9, because the negative times the negative is a positive, right? So basically everything in parentheses that started positive became negative, and everything in the parentheses that was negative became positive, okay? So now I don't have to worry about that negative sign, and I can just start combining like terms. 11x to the fourth minus 2x to the fourth is 9x to the fourth. Cross those out. Negative 9x squared does not have anything to combine with on the right, so we're going to just leave that as negative 9x squared. 3x minus 2x is 1x plus 1x. And 11 plus 9 is 20. And then we still have that negative 6x cubed that we didn't combine with anything on the left. Note, this is not in standard form, so let's rearrange it to make sure it's in standard form. Note, I did not put a 1 in front of the x here. You don't have to. 1x is just x. You can just write x. All right, great. Now we're multiplying these two polynomials. Okay, so multiplying polynomials is not that challenging. Just pay attention here. So the first thing you'll do is you'll multiply the first term on the left by the first term on the right. X squared times x squared is x to the fourth. Okay. Then you'll multiply the first term on the left by the second term on the right. Okay, so x squared times negative 3x is negative 3x cubed. Then you'll multiply the first term on the left by the third term on the right. X squared times negative 5 is negative 5x squared. And then you do that again for the second term on the left. The second term on the left times the first term on the right. Negative 2x times x squared is negative 2x cubed. Then you do the second term on the left times the second term on the right. Negative 2x times negative 3x is positive 6x squared. And then you do the second term on the left times the third term on the right. Negative 2x times negative 5 is positive 10x. Okay, what do you think you do next? The third term on the left times all three of those terms, right? So times this one, and times this one. I'm just going to go faster. So negative 4 times x squared is negative 4x squared. I'm going to run out of room here. Let's adjust this. Negative 4 times negative 3x is positive 12x, and negative 4 times negative 5 is positive 20. Okay, great. Now you just want to combine all your like terms. Okay, so are there any more x to the fourths than just x to the fourth? No, there are not. So that stays as x to the fourth. Negative 3x cubed and negative 2x cubed. Those become negative 5x cubed. Okay, let's cross out what we've used. Negative 5x squared, 6x squared, and negative 4x squared. That becomes negative 3x squared. Yep, negative 3x squared. Great. 10x and 12x become 22x. And then 20 is just on its own. There's nothing to combine it with. So there you go. There's your multiplied polynomial. The product of those two trinomials. All right, and the last thing we're going to look at is this thing called the binomial expansion theorem, which makes use of Pascal's triangle. Now, you may have seen Pascal's triangle before. It looks like this. It starts with a 1, and then you put 1s on either side of that, and then you go 1, 2, 1. The 2 comes from the fact that you're essentially adding these two numbers together. Okay, the row after that is 1, 3, 3, 1. The 3's come from 1 plus 2 is 3, 2 plus 1 is 3. Okay, and so forth. So then it's 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And you can keep going, right? The row after that would be 1, 6, 15, 20, 15, 6, 1. Okay, so here's how it works. So if I have a binomial like x plus y to the power of 4, okay, this would become 1x to the fourth y to the 0 plus 4x cubed y to the 1 plus 6x squared y squared plus 4xy cubed plus 1x to the 0 y to the fourth. And I know that that's super confusing, but here's what's happening. So essentially what I'm doing is these coefficients here, 1, 4, 6, 4, 1, those come from this row of Pascal's triangle. Okay, so this row, the top one is for powers of 0. The second one is for power of 1. The third row is for power of 2. The fourth row is for power to the third cubed. The fifth row is to the fourth. Sixth row is to the fifth. Seventh row is to the sixth. Okay, so what do I mean by that? I mean by if you're a binomial, whatever the exponent is out here, that tells you what row you need to go to. Okay, so we had an exponent of 4 out here, so that means we need to look at the fifth row of Pascal's triangle. If this had been an exponent of 5, we'd need to look at the sixth row of Pascal's triangle. But because we had to the power of 4, we're looking at the fifth row of Pascal's triangle. Now, what do you do from there? Well, that tells you that your expanded binomial is going to need to have 1, 2, 3, 4, 5 terms, where each of these numbers is the coefficient of each term. Okay, and so this is how it works. Let's go through it slowly again. So I know because I have to the power of 4 here, I need to look at the fifth row of Pascal's triangle. So what you do is you start with the first number of that row, 1, and then you take your first variable, x, you raise it to the power of 4, and then you put your second variable and you raise it to the power of 0. Okay, then you add that to the second number in the row of Pascal's triangle, which would be 4 in this case. You take 1 away from your first variable, and you give that exponent to your second variable. So notice how we started with 4 and 0, now we're at 3 and 1. Those still combine up to 4. Then for your next term, you take the next number in that row for your coefficient, and you take 1 away and you give 1 again. And you just do that on until you end up with no terms left. Like that. Okay? So practice that a couple times. I know it's a little confusing, but it's not that bad. Now, one thing that's important to note is, let's say that this had been a 2x inside parentheses here. Look how that changes. So it becomes still 1 from the number outside of Pascal's triangle, but then in parentheses, it's 2x to the fourth, y to the 0. Okay? That parenthesis is super important because what does that mean? That means that the exponent is going to the 2 as well as it is to the x. Okay? So 2 to the fourth is 16, right? So this would be 1 times 16 x to the fourth, y to the 0. So make sure if there's a number inside with the variable, make sure you're giving the exponent to that number as well as to the variable. Okay. All right, let's look at an example here. G plus 2 to the fifth. So I'm going to draw out my Pascal's triangle really quick. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1, 1. Cool, so because my exponent is to the 5, that means I need to go down to the 6th row of Pascal's triangle, which I've just ended with here. And so this is going to be 1 times g to the 5th times 2 to the 0, plus 5 times g to the 4th times 2 to the 1, plus 10 times g cubed plus, or sorry, not plus, times 2 squared, plus 10 times g squared times 2 cubed. I'm going to go down here, plus 5 times g times 2 to the 4th, plus 1 times g to the 0 times 2 to the 5th. Okay, and then you can just simplify everything. So 1 times g to the 5th, 2 to the 0 is just g to the 5th, plus 5 times 2 to the 1 is 10, g to the 4th, 2 squared is 4 times 10 is 40, 40g cubed, 2 to the 3rd is 8 plus 80g squared, 2 to the 4th is 16 plus 8 is 80 again plus 80g, and then 2 to the 5th is 32 plus 32. So there you go, right? And why is this useful? Because it would have taken a lot longer to try to multiply out all 5 of those binomials than just using this expansion theorem. And there you go. That's how it works.